Hi, I want to talk to you today about the pendulum. And you're all familiar with what a pendulum is, something that you just swing back and forth. It's got a ball connected to it. That ball is actually often called the bob, like the name Bob, B-O-B, except I can't spell B-O-B. And I'm not going to get into this mathematically, but I'm going to talk a little bit conceptually and about some of the forms of energy, for example, transfer that go on, which is where these are going to come into effect in a couple minutes. But let's start with a couple definitions. The period of a pendulum is just the time it takes to complete one full swing. So if it starts here, one full swing would be there and back. And because it's time, you're measuring it in seconds. Now, you could run an experiment, for example, to see what sorts of things affect the period of a pendulum. And it's very common for students to think that a more massive pendulum, for example, has a shorter period. That because it weighs more, it will swing back and forth more quickly. But if we test that, it actually turns out not to be the case. Mass does not affect the period of a pendulum. A bigger bob does not affect the period of a pendulum, unless perhaps you take air resistance into account. And part of the reason for this is that if you measure the acceleration of falling objects, you find that big or small, if you ignore air, if you're in a vacuum, everything falls at the same acceleration, 9.8 meters per second squared. So attaching a rope to it shouldn't affect that either. They're all basically falling at the same rate. Now obviously, the rate at which they fall is different than 9.8 meters per second squared because it has a rope attached to it. But adding the rope doesn't affect the fact that they all fall at the same rate. Now you might also think that release angle has an effect, and it turns out it does not. Although I'm going to say if you test it in real life, you'll actually find a small difference for different release angles on the effect on the period, and it really all comes down to the friction at the point. Having a bigger release angle gives you like a longer amount of friction, a longer swing. But if you had a frictionless pendulum where there was no friction up here, the release angle wouldn't make a difference either. The one thing that does make a difference is length. L-E-N-G-T-H. So longer equals a longer period. And this should be something that makes sense to you intuitively. Like if you have a swing, for example, on the playground, it's a pretty long pendulum and it takes a bit of time to swing back and forth. A very short pendulum swings back much more quickly and thus has a very small period. Let's talk about energy transformations too. So a pendulum has what we're calling a restoring force. And that restoring force is a force that tries to restore the pendulum to equilibrium. And this right here, I'm just going to put E there, that's your equilibrium point. You could put a pendulum down here and just let it sit and it would stay still. But you cannot put a pendulum here and let go and expect for it to stay there. It just doesn't work like that. This is the equilibrium point. So when you have a pendulum here, the force is trying to get it back down there. If you have a pendulum here, the force is trying to restore it to the equilibrium point. But at the equilibrium point, it has zero net force and thus zero acceleration. It's at the pendulum point, at the equilibrium point. But what it does have is velocity. So it's swinging quickly enough that it's going to keep going past the equilibrium point. So what does this mean? If it's got maximum velocity, it means that it has maximum kinetic energy. It's moving pretty darn quickly for a pendulum. It's also lowest here, so the potential energy is going to be a minimum. Won't be zero because it's above the ground, but potential energy is still minimum. As opposed to up here and up here, where potential energy is maximum because it is highest off the ground. Other things that you see is that the force, the further you get from the equilibrium point, the bigger the force. So the force is going to be maximum, and thus the acceleration is also maximum. At both this point and this point. And those are very similar in terms of the actual physics. This pendulum actually stops for an instant up here, so your velocity is 0 at both points. And thus, if your velocity is 0, your kinetic energy is 0. Let me get 0 joules, 0 joules. So this turns out to be a conservation of energy problem, in that what you have happening is that your total energy is constant for the entire thing. So if you had 30 joules up here, you have 30 joules here, you have 30 joules here, you have 30 at every different place. But some of that potential energy, which is maximum up here, gets changed into kinetic energy down here. So it's a transformation of kinetic and potential energy. So throughout a pendulum problem, if it's frictionless, you have conservation of mechanical energy. And you can actually work this out through the entire problem, just like you did, for example, with the roller coaster problem. And you could even find the speed, for example, if you knew the mass. This is an introduction to pendulums. Thank you very much for watching.